Hello, everyone. My name is Eduardo Serna. I'm gonna be giving a talk on random sampling in the Wolfram language. This will be hopefully the first part of a series of talks from our team, the Probability and Statistics group in Wolfram. I'm a consultant there. The other half of my team is Gosia Konverska, who's hopefully around but will be helping me answer questions today, if there are any, and will be giving some of the talks in this series. So the first talk is going to focus on univariate distributions, and this is the outline of the talk. This is a very, very big subject, and I've chosen the aim of the talk, I guess, is to balance between it being informative. So I will try and hopefully expose the functionality that is available in the Wolfram language. I'm going to try and make it educational. So give you an idea of the different methods and techniques that are used in sampling. And I'm also going to try and make it entertaining. And this is obviously very subjective, but from my point of view, I am a physicist by training. That was very interested in probability when I was a physicist, and this is by far my favorite part of my job here at Wolfram. The random number generation is very, very fun for me, and there's lots of very interesting math and computing that goes into generating these elusive things, which are pseudo-random numbers. So the outline of the talk is I'm gonna first talk about uniform RNGs. I then talk about continuous distributions, introducing the different techniques that are available to us. And this is by no means exhaustive at all. And I've left some very big methods here, but those are for follow-up talks. So I'll talk about functional transformations, inversion as an example of it, acceptance-rejection, use these methods to introduce how one samples from discrete distributions, and then that's going to be me. So randomness is what it means for something to be random is actually kind of quite a profound concept, and it's not entirely obvious, and loads of mathematicians and physicists and philosophers have discussed it. But from a physicist point of view, I think a useful way to think about this is to look that we have some complicated process that we're not privy to all the internal details, the internal states, and we're just looking at some cross-section of it, where we have we would call them observables in physics, and we have, from the point of view of those observables, we've averaged out, we integrated out all of the internal state, and we just get something that looks random. Essentially, it's not intrinsically random. If we had access to everything, it wouldn't be random. We would be able to see exactly where everything comes from, but because we don't have access to all the internal details, it looks random. And computers are largely deterministic. There's some issues about like cosmic rays and cache races and stuff like that, but they're mostly deterministic. And so generating a pseudo-random variable from a computer is A, not entirely obvious, but B, we can use essentially a procedure that one could think is inspired by nature, and just it involves transformations to just garble the inputs in the internal state enough that we lose track of where we started. And we start the building blocks for producing random number generators are uniform random number generators from a pseudo random distribution, and they're the building blocks that we use to build more complicated samplers from non-uniform distributions, processes, spatial distributions, etc. And we want them to look as random as possible, while at the same time balancing other factors, such as crucially speed, but also memory and simplicity of the, and other useful things such as reproducibility is a key aspect, because with computers, we kind of want to have our cake and eat it too, and we also want to be able to reproduce the results by controlling the seed of the, what's called the seed of the random number generator. And here we have random real is a function that generates reals from a uniform distribution here between 0 and 1. We compute a million, we plot the histogram, and we see that it's essentially uniform with small jitters that are plausible and reassuring. These jitters are what this histogram would look essentially the same if this was a true random number generator and not a pseudo-random number generator. Okay, so in Wolfram language, I have a family of functions to sample from different uniform, different types or different tasks in this case. So we have random integer or real or complex for numbers. We have random choice and random sample for lists with or without replacement. We have primes for prime and numbers, and more esoteric stuff like random color, random image, etc. So let's look at two very important aspects of the framework here, which is to be able to specify the seeding. As I mentioned earlier, we want to specify this, be able to specify the seeding, because we want to be able to get reproducible results. This is important, because sometimes we've used the random number generator in a computation, and we want to go back and run it back by essentially specifying the same seed and make sure that nothing funny is going, or we understand the computation. And this is done in the Wolfram language by using seed random. Once we specify the seed, all of the following the random numbers that are computed following that seed will be the same. So if we do the same thing twice with the same seed, we will get the same random real. Another very important thing that we can do is to leverage the arbitrary precision arithmetic system in the Wolfram language to be able to get arbitrary precision, random arbitrary precision numbers that have more random digits that are allowed by the hardware. And this is again very useful for certain computations where things might be ill-conditioned, or what you're close to a singularity, and there's no algorithm that will save you from that, and you just need more digits than those that are available. And machine precision, which here I generate the random real, and the precision is machine precision, and that's about 16 digits, decimal digits, but I can generate 24, and then we would be able to use these to compute at 24 digits. This is, of course, more expensive, slower, but it's sometimes needed, and it's very important to have the option. Another nice aspect of the framework is that you can plug in your own custom uniform random number generator. And here's a reference that is very complete, and it talks a lot. It's has much more information than I'm going to give in my talk. It talks a lot, but a lot of what I'm talking about, the references are there, and in particular, it's very detailed on how to plug in your own generator. I'm not going to go over all of the details. I just wanted to show an example of one generator you can plug in, which is PCG. It's the permuted congruential generator. It's a relatively recent algorithm that has appeared recently, It has very strong statistical properties, and among other nice things like look ahead, and it's very light and simple. And I wanted to bring it up because it has, well, first of all, it's state of the art. So it's possibly in many ways the best one there is. We haven't had time to add it, but we really should add it to the family that we support natively. And it has it's also very simple, and you can see some of the aspects that I was discussing earlier, where you just have a state, and you have a state, and you garble it a little bit, do some computation with it that mixes it about, and the state is bigger than the thing that you're going to be returning. The result in this case has a bit width that is the state is twice as big as the result. So you do some operation on the state, and then you do some further operation that is just bit operations that are mixing things about, XORing, shift righting, rotating right, and then you return the result and the new state. And this is essentially the heart of the code of this generator. And as you can see, it's very, very simple. This code is just to make sure that we have the correct bit width. And I'm not gonna show the rest of the boilerplate that involves in plugging it in, but that's the heart of the generator. And we can see that if we just specify the method to seed random, this is how you once you've defined the code, you specify the method to seed random, and we can generate 10 to the 4, and it looks entirely reassuringly plausible. There's more jitters now because we only have 10 to the 4. The size of the sample is only 10 to the 4. Okay. Another thing I wanted to point out is that there's loads of very, like this in this reference, there's loads of different built-in samplers that you can use, and in particular, there's some that can be useful for very specific tasks, like the low discrepancy ones, that are ones that have like a lower quality of statistical properties, but the trade-off is that there's more spread out the numbers that they produce, and that could be useful for certain for certain numerical tasks like integration. Okay, so let's look at now at non-uniform random number generators, and to sample from in the Wolfram language, to sample from non-uniform random number generators, we can use random variate. Random variate, which works for both continuous and discrete distributions. So here we have the normal distribution, which is the most canonical one. The continuous distribution, also called the Gaussian or the bell curve. We sample 1 million data points, and the histogram looks like it should. The blue line is the PDF, and the histogram is bell-shaped. We can also sample from discrete distribution, like the Poisson distribution. And here we're plotting we call it the PDF. It's the same function, but it's actually for discrete distributions. It's technically called the probability mass function because it's only defined at discrete integer points. And we see that the histogram agrees with the Poisson PDF. There's a question here. Okay. Had that a link exists between number theory and probability theory? I believe in regards to prime distribution. I'm not an expert of number theory, but okay, yes, there's some random measures that you can define on these prime distributions. Yes, I will discuss it. I think I'm gonna discuss it later if I have the time. Okay. Okay, let's keep going. Okay, so let's talk about functional transformations. So the next step, I guess, is to generate samples from a non-uniform distribution using uniform random samples. And to do so, we gonna have to define the CDF, which is the cumulative distribution function, and it's a function that just describes how much probability there is up to a certain number. So it's the CDF is denoted by capital F of a random variable capital X, and it's a function of a number X, and it just counts how much probability there is when the random variable is equal or smaller to a certain value. And here I show this is the PDF of the Gaussian that I showed earlier, and it has the density, the probability is all in close to the center, and the CDF, sorry, is a function that actually interpolates between 0 and 1 from -infinity to infinity, and it just counts how much probability has accumulated as you go to the right. Technically, the CDF is the integral of the PDF, but it's actually much more general because sometimes the PDF is not defined, like for instance for discrete distributions. So it's better to work with CDFs. And this formula allows us to construct random variables by applying a function to other random variable. So if we have a function g and we use it to define a random variable y, we can try and figure out what's the distribution of y. And this can be seen by just applying the definition that g of x is smaller or equal to small y here. And to express this in terms of the known f of x, of the CDF of x, we need g to be invertible, because if it's invertible, we can just apply to both sides of this inequality, and we will get x, random variable x on this side, and g minus 1 of y on this side. And this is actually the definition here. As we saw, this is the definition of something of x, small x of the CDF of x. So there's two possibilities. For g to be invertible, it has to be either strictly increasing or strictly decreasing. There's two possibilities. If it's strictly increasing, then this inequality doesn't switch sides, and we get that the CDF of y is CDF of the g minus 1, the inverse of this g transformation on y. If it's decreasing, we use the fact that if to one side of this inequality, there's 1 minus the amount of total probability of the other, so we switch. So we just can call this 1 minus the CDF of g minus 1 of y. Okay. And we can use this transform distribution to figure out the distribution of these transform random variables. Transform distribution takes an expression and variables that are distributed. This symbol means distributed as certain distributions, random variables, and it can figure out what the output distribution is. So for instance, if we use a simple invertible function like the minus log, we will find that on a uniform distribution, we will find that this has transform distribution knows about this one, which is the exponential distribution. And we can see that the CDF is essentially 1 minus the inverse of this log that I used here. And this is a valid way to sample from it's not the one we use, but this is like fast enough. So we can generate 10 to the 7 uniform. This here I'm explicitly using uniform distribution, but this could have been random real 10 to the 7 is exactly the same thing in this case. And we take the log of that data, flip the sign. This is all fast because these are vectorized operations there, which means the machine operates on the whole data at a time, not one by one. And we see that the data is indeed distributed like an exponential distribution. This is the PDF of an exponential distribution. Okay. So let's look at what's called the inversion formula now. So what we actually want is to generate samples from a distribution D, having access to samples from the uniform distribution. And we want to figure out, so what's the G that we need to apply? What's the transformation we need to apply to get there? So for a uniform random variable, I hope it's not hard to see that the CDF takes the following form. It's just the identity function. And this can be seen by looking at the PDF, which is just a horizontal line because it's the same everywhere. That's what uniform means. And the integral of that, the CDF, is essentially the linear function x with slope 1. So once we have that, once we have access to the CDFs of U and the one we're looking for, x, we can use the inverse of x, the inverse CDF of x as a transformation function G to construct variables that are distributed as x. So here this is the formula I used before for transforming functions, and we just replace z here with u, g with f minus 1 of x, and we substitute and we get that the CDF of y is indeed the CDF of x. So x and y have the same distribution. This means that by applying the inverse of the CDF of x to a uniform sample, we obtain samples from x, which is what we wanted. Okay. So let's construct samples from the normal distribution using its inverse CDF. The CDF of the normal distribution is called the ERF function, and it's essentially the integral of its PDF, and the inverse distribution, its inverse function is the inverse ERF, and these are not elementary special functions. Elementary being not used very often, I guess, and as such, they're much more slower to compute than, say, the exponential. And this is an issue because although we can use this inverse to, again, apply to uniform random variates and apply the inverse, we will get samples from the normal distribution. It's actually quite slow. This is because the inverse ERF is, even though it's vectorized, it's relatively slow. So as we saw in the last slide, evaluating certain inverse CDFs can be actually quite expensive. However, there are all sorts of clever transformations to sample from important distributions, and I'm gonna look at one which is called the Box-Muller Transform now, which is important because it's the one that we use and one of the most canonically used to sample from the normal distribution, which is very important. And also, I chose it because it has a very clever trick, in my opinion, that is quite fun. So what it does is it uses the observation that the square root of a sum of the square of two random variables that are normally distributed has a CDF that is easy to invert. The transform distribution is Rayleigh distribution with parameter 1. This is not very important. What's important is the CDF. This CDF can be inverted using elementary special functions. The elementary special functions are the exponential, the log, the trigonometric ones. Those usually have been optimized by, I guess, the computing community for like decades now, and very often have hardware support to some extent. So they're essentially implemented at the CPU level, and this makes it much faster. Okay. So we're now going to use basic trigonometry to see how the Box-Muller transform works. So we have seen that by this is an expression of the Pythagoras theorem, but Pythagoras theorem essentially says that the square of one side of a right angle triangle, one side plus the square of the other, is the square of the hypotenuse. And that's essentially the transformation we were doing here. So we knew that if these two sides were distributed normally, this radius of the circle here would be distributed as the Rayleigh distribution. So now we can go the other way. We can use this to compute first random variables from the Rayleigh distribution, which we found were cheap to compute, and then use trigonometry to project onto the sides of this triangle using the cosine and the sine, and we will get using an auxiliary random variable for the angle, which is uniform. If the angle is uniform, the sides of the triangle will be normally distributed, and this can be seen by performing transform distribution on a Rayleigh distribution times the sine or the cosine of an angle that's distributed uniformly, and we do indeed get the PDF. This is the PDF of the, I'm going a bit slow, the PDF of a normal distribution. Okay. So another reason I wanted to show the Box-Muller transform is actually this code is trivial to do, and it can run very, very fast at top level as well. So this is the procedure we talked earlier. We generate pairs of random variables, uniform random variables. One of them we choose to compute the radius, and then the other one we use to compute the angle, and we project onto x and y, and this gives us pairs of normally distributed random variables, as we can see before. And this is computing 2 times 10 to the 7 pairs, as opposed to 10 to the 6 for the inversion formula. So this is over 650 times faster. Okay. So now let's look let's look at another very general method, which is called acceptance-rejection. And in its simplest form, it uses 2 uniform random numbers per sample. Suppose the Box-Muller was using 2 and giving you 2. This is using 2 and giving you 1. However, if most of the cost of generating these random numbers is in these transformations, so as long as these transformations are cheap enough, this is fine. And these methods can be very fast and efficient. So we use one of the pair of uniform random numbers to propose a possible sample from a hat distribution. And the other pair we use to compare to the ratio of the PDFs. Between the target distribution and this hat distribution, this proposal distribution. And we accept the proposal if it's appropriate. So let's sample from a trapezoidal distribution, for instance, with a uniform hat. And here I'm introducing the trapeze is defined here as a piecewise, and I'm introducing probability distribution, which is a container for general purpose user-defined probability distributions. And because I haven't bothered to normalize this, this f doesn't integrate to 1. if I specify method normalize, the system will take care of the rest and compute the appropriate coefficient. Okay, so here is what the PDF of the trapezoidal distribution looks like, and this is the hat that I've chosen for it. And it's important to note that here this is a toy problem, but in reality we really want the hat to be as tight as possible to the all of this blank space here is not very good. We also want to balance with the fact that we want sampling from the hat has to be easy to do. Here it's very easy because it's a uniform, but what you're balancing here is having a hat that is as tight as possible, but is as simple to sample from as possible. And let's write a very simple algorithm that I can show here. We generate again 10 to the 6 pairs. We're going to use this dynamic array just to store the accepted proposals. And what we do in the algorithm is we just specify a proposal, which normally would be a transformed, wouldn't be a uniform, but would be a sample from this hat. Then we use this P to compare to. This will be a uniform usually in the algorithm, and we compare the PDF of our target distribution, the proposal, with divided by the PDF of the hat at the proposal, which is, in this case, it's a constant because it's uniform. And if it's bigger than P, we append. We do this in a loop, and we get the samples that we can see here, the histogram overlaid with the PDFs, and we see that it follows quite nicely. But we also see that we've essentially thrown away 30% of the proposals. And this is indeed the ratio of the volume of this PDF here, the hat, compared to, the target distribution, which here is 1 because it's normalized, to the volume of the hat here. So that's why we usually want this hat to be as tight as possible, because we don't want to be throwing away 30% of our proposals. Okay. So the probability distribution we saw earlier is a general container for use of define functions, and it has several sampling methods available, including acceptance-rejection. And this is true for other built-in distributions as well, but the built-in distributions has optimized custom code that is optimized for both speed and correctness. So we wouldn't want to use these algorithms, general purpose algorithms, for the built-in cases. But if you're defining your own probability distribution, these can, and you, for instance, want to use acceptance rejection, and you define a suitable hat, this can be a very fast and efficient sampler. So let's look at an example where we have like the product of two sinusoidals divided by 1 over x squared. Essentially, the sinc function is sine of x over 1 over x. And this complicated distribution that I plot here, the orange one, has a very natural hat, which is just the envelope of the sinusoidals, which is the 1 over x squared. And we can just truncate it here when it reaches close to 0, and have a uniform distribution here. So I am gonna, and here's the piecewise. It's constant close to the origin, and it's 1 over x further out. So from this hat function, we can plug in this distribution to random variates, select the method acceptance rejection, the sub-option hat function. You could also provide a sampler for the hat function, which makes it even faster. Not needed in this case. I'll use other methods like MCMC, which I'll talk about in a different talk. But this is already pretty good. And I'm showing the log PDF to show more detail. Otherwise, it all gets squeezed near the origin a lot. And so this works really nicely for this complicated. It's actually pretty good. Okay, so I'm almost out of time, but I'm almost done. So let's talk a little bit about discrete distributions now. And I'm going to show that like a lot of the same algorithms I've been talking about apply, although sometimes they're a little bit more complicated because we're trying to sample from integers, so we try to transform some uniform random numbers in the real line and truncate them to integers, and that has some subtleties. Like for instance, in this algorithm by Knuth, which is not one that is used by anyone today, but I'm choosing it here because it shows some of the things I want to talk about. So the PDF of the Poisson distribution looks like this. It has a constant factor, there's an exponential, and then it has an exponential with base lambda and divided by a factorial. And we've seen the PDF of PMF of the exponential before at the beginning of the talk. And here we can see that the algorithm by Knuth is very, very simple. We define some constants, and then we iterate in a loop. Multiplying in each iteration, we specify a uniform random number, we multiply it, and when this accumulated product reaches a threshold, we just return the number of the iteration, how many iterations this loop did. And we can see that this indeed gives the same as before with the built-in sampler. This gives the right result. Actually, there are subtleties here that I'm glossing over, like for small enough lambda, for specific values of lambda, this algorithm will have numeric problems. But this is good enough for now. It's a toy problem, and it's a toy algorithm that I wanted to be able to show the code. However, if we want to have a look at the real thing, which is what we're using in our system, it's a much more complicated algorithm. It switches between inversion and acceptance-rejection, and for different ranges of the parameter lambda. The acceptance-rejection algorithm is a very clever algorithm by Arens and Dieter, which uses a discrete normal hat function, and this hat function is above the Poisson density on one known side of the range. Like on one side of the range here, up to here it's below, and up to here is above. So you can split the range in two, compute a certain constant to majorize these numbers, and then we can use that. And these hat function will actually be very, very close to the actual PDF. So this algorithm will be very efficient and have very few rejections. So I showed a toy implementation of the algorithm, but different facets of acceptance rejection. I had a sketched an outline of a more complicated use of acceptance rejection in the Arens-Dieter implementation for the Poisson. But acceptance rejection is used in most sampling algorithms, and they can get very clever and be very efficient. I showed that it becomes expensive when one of the ways it becomes expensive is when the hat gets very far away from the density, when it's not tight. And this unfortunately happens inevitably at higher dimensions due to something called recursive dimensionality, which is the fact that a lot of them in a higher dimensions, a lot of them measure in a shape, a lot of the volume in a shape is near the boundaries. And that's why for in high dimensions, very quickly, one has to use different algorithms, mostly MCMC, Markov chain Monte Carlo, which we'll discuss in another talks, because we mostly use it in other parts of the system, not so much in univariate samplers. Okay, so closing remarks here. I haven't been looking at the questions because I'm a terrible person. Yes, this is a huge subject. We're just scratching the surface. I just wanted to like whet the audience's appetite here. I think it's very, very fun, and that might be just me. And I deliberately avoided talking about MCMC because this is better addressed in different and subsequent talks that will be given by myself and Gorsia. Okay. Thanks so much for listening. Yeah, thanks so much. This is I'm done with the talk, and now I can hopefully maybe answer some questions. Okay. Okay, so it's Rachel Hyman, Andrew Yu. Okay. So let me go in order. So the link between number theory and probability theory, yeah, there's actually quite a lot. And again, I don't know enough about number theory to really answer this authoritatively, but I've read about it. It's just like also like it's a very big topic, and I'm not sure I could answer this well enough in the time that we have here. Okay, Andrew Yu. Okay, this is topic for probability. Any plans with the stats theme of incorporating penalized regression, low S? Regression is in the pipeline, but it was definitely talked about it. I don't know when it's going to be done though, but we definitely want to revamp regression. That's something that we talked about. Generalized additive models, not so much. When are we going to talk about MCMC? I don't know. I'm guessing there's other people that want to present. I imagine not immediately, but I don't know. We've prepared some of these talks already. That will be a question for Charles, I guess. Okay. So that seems to be it, I think, question-wise. Okay, unless I'm missing something. Okay. Okay, thanks so much. I hope this made some sense to you guys and also was interesting, because that was the point. So yeah, goodbye, and thank you so much for listening.